welcome. We are discussing about measurement of resistance, and so today we will start our talk with Wheatstone bridge, which might be familiar to you. Okay. So the bridge looks like a square, and we have four resistances, call them P, Q, R, S. We connect power supply across two opposite terminals. So, this is DC supply because we are measuring resistance, okay. And we connect a galvanometer or any null detector D across the other two terminals, and then you know that if the ratio of P by Q is same as R by S, then the potential at this point and at this point will be same. So, no current will flow through the detector. So, that is called the null condition. Okay. So, this is the null condition. Okay. Now, with this we can measure an unknown resistance. Suppose this R is unknown and we want to measure the value of R, and say this P, Q, R, S, these are known and variable resistances. So, we can set up a bridge like this. R is unknown and these three resistances we can change. So, we can change these three resistances so that null condition is achieved. The galvanometer shows no deflection, and then this condition is, this balance condition is true, from which we can write R is equal to P S by Q, where P, S and Q are known resistances. So, we know these values, so R can be found. So, this is very simple. So, today we will talk about accuracy, precision and sensitivity of this Wheatstone bridge. So, let us talk about the accuracy. If say suppose these resistances P, Q and S, which are known, they are they have an accuracy or error of like say P is 1% accurate or inaccurate, Q is say 2% accurate, and say S is 3% accurate. Okay. So, if this is the case, and say at balance we observe that the value of P, S and Q are say respectively like say 5 unit, then maybe 2 unit and maybe 4 unit. Okay. So, this means R is equal to 5 into 2 by 4. So, this is the estimated value of R, which will be 2.5, but there is an uncertainty. There is an uncertainty in this measurement, because the values of P, S and Q, those are not accurate. We see that the value of P is 5 ohm, say according to the marking or dial of this resistance box, but it has an accuracy or error of 1%. So, that means the value of P is actually 5 ohm plus minus 1%. So, which is like so this is 5 plus minus, so 1% means 0.05 ohm. Okay. So, this is the range of P within which P must lie. So, P must lie between 4.95 ohm and 5.05 ohm. Similarly, we can, so this is S is 3% accurate, and similarly Q is 2% accurate. So, they have a range. Okay. So, similar like Q is 4 plus minus 0.08 ohm and so on. Okay. So, what is the limiting range of R roughly? What is the, so R is estimated to be 2.5 ohm, but it is not exactly or not necessarily 2.5 ohm. It has a range within which R should lie, and what is that range? So, if you recall, yesterday we have seen that the relative error or percentage error gets added in products and ratios. Okay. So, here R is estimated as the product of PS divided by Q. So, therefore, the relative error or percentage error in measured value of R, that will be given by percentage error of P plus percentage error of S plus percentage error of Q. So, which is for 1% for P plus 3% for S plus 2% for Q, which is 6%. Okay. So, that means R should lie. So, R should lie between lie between 2.5 ohm plus minus 6%, which is okay. So, this is like 2.5 ohm plus or minus 2.5 into 6 by 100 ohm, and you can calculate what this value is. So, it is not exactly 2.5, but it is around, it is somewhere near 2.5. It is within 6% deviation from this estimated value. So, this is about the accuracy of this measurement. Okay. So, now let us talk about the resolution of measurement. So, what do we mean by resolution? Okay, so, possibly this is a new terminology we are introducing now. So, let us define resolution with an example. Suppose I have a meter, say a voltmeter, which has a range of 0 to 10 volt, and say it has 100 divisions. Okay, so, say it has small divisions and a total of 100 divisions or 100 markings on this scale. So, 100 divisions. That means each division of this voltmeter is equivalent to 10 volt divided by 100. Okay. So, it is 0.1 volt. Now, if the pointer is say here, maybe this indicates a value of 6 volt, and then the immediate next marking, this will indicate a value of 6.1 volt. So, the pointer can indicate values in multiple of 0.1 ohm, and this is you can call as the list count, or we call it the resolution of this meter. So, the resolution of this meter is 0.1 volt. Now, coming back to our Wheatstone bridge. Okay. So, we had unknown R is equal to PS times Q, and so, okay, this is the diagram. Let us draw it very quickly. P, Q, R and S. Okay. So, I am not drawing the power supply and the detector now. Okay. So, observe and say, suppose that P and Q are constant resistances. Okay. Say P and Q are fixed resistances, and S is a, say, decade resistance box, whose such that S can be varied in steps of, say, 0.01 ohm, maybe, or maybe say 0.1 ohm. Okay. So, S can be varied in steps of 0.1 ohm, but P and Q, they are fixed resistances. If so, then the value of P and PQS, they were 5 ohm, 4 ohm and 2 ohm. Now, these two are fixed, and this can be varied in steps of 0.1 ohm. And then R is given by P by Q. So, from here multiplied by S. Now, P is a fixed number, Q is a fixed number. So, this is a fixed number. So, therefore, we can write this P by Q, which is 5 by 4. So, that means this is 1.25, okay, multiplied by S, and this S can be varied in steps of 0.1 ohm, and this is constant fixed, and this is variable in steps of 0.1 ohm. Okay. Now, so during the experiment, what do we do? So, we keep these two are fixed, not variable. We vary this S in steps of 0.1 ohm until and unless we get least deflection in this detector. Okay. So, in this detector we observe the deflection and vary the value of S until and unless we have minimum smallest amount of deflection in this detector. So, we are varying S. Now, S can be varied in steps of 0.1 ohm, which means this quantity, okay. So, this quantity together, so this is varied in steps of 1.25 multiplied by 0.1, which is 0.125 ohm. Okay, 1.25 multiplied by 0.1. So, this is the minimum change that you can create in this quantity. So, for example, when S is if S is, let us make a table, value of S and the estimated value of R, which is this PQ by S. Okay. So, if we take S is equal to 2 ohm, then this will be from this it will come out to be 2.5 ohm. Next, you can take S as, and you can observe deflection. Then you take S as say 2.1 ohm. This is the minimum change you can make in S, and then the value of estimated value of R will be 2.5 plus this quantity. So, which will be 2.1 2.627 ohm. Okay, and you observe the deflection. Suppose you see more deflection here, here it is less, then this is a better estimation. Okay, but you can change the your estimation only in steps of 0.125. So, this is the resolution. So, we call this as the resolution of the meter, which is 0.125 ohm. Okay. So, now so we have talked about resolution and accuracy. Another important quantity we will talk about is sensitivity. So, what do we mean by sensitivity? So, this is the bridge. So, where we have say P, Q, R and S. Detector, and the chosen value of P, I mean for this example is 5, 4 and 2, 5 ohm, 4 ohm and 2 ohm. So, R came out to be 2.5 ohm. Now, under this situation there is no deflection at all, because the voltage here is same as the voltage here. But suppose this unknown R, or this measurable quantity which we are measuring is changed. It is changed by a small amount. Okay. Say R is changed by a very small amount. Is very small, say like maybe 0.0000001 ohm, so small as you can think. Now, of course, if you change by even by a small amount, now this P by Q is no longer equal to R by S, because R is changed. So, these two potentials at these 2 points, they will no longer be same. So, some current should flow to through the detector, and we should observe a non zero current. But if this change is very small, then the change in potential here between these 2 points will also be very small, and the current through this detector will also be very small, and we may not be able to observe that change. Okay. So, if the change in unknown quantity, which is R, is very small, then we may not observe any deflection, because the current through the detector will be very small. So, we can ask a question, what is the minimum change in R, that is the unknown quantity, quantity being measured, so what is the minimum change in R that we can detect? Okay. So, this question we may ask, okay, and say if delta R is the minimum change, minimum of detectable change, then we say that the sensitivity of measurement is delta R. Okay. So, the minimum change in the unknown which we can detect, which we can measure, not measure, which we can detect or observe, is called the sensitivity of the measurement. If delta R is, if say delta R is equal to 0.0 or say 0.1 ohm, that means we can distinguish between 2.5 and 2.6 ohm. With the value of, if the value of R is 2.6 ohm, there will be some observable current here, and the bridge we will say is not balanced. But if it is 2.5 ohm, then no current flows. So, we can differentiate between the value of R equal to 2.5 and R equal to 2.6, but we will not be able to distinguish between R equal to 2.5 and say 2.55, because then, so if delta R is 0.1 ohm, so this is the minimum detectable change or sensitivity, then for both, so then we cannot differentiate between, then we cannot differentiate between R is equal to 2.5 ohm and say R is equal to 2.55 ohm. Because with R equal to 2.5 ohm, no current flows through the detector, and with R equal to 2.55 ohm, such a small amount of current flows which we cannot detect. That say that the pointer doesn't move at all, we cannot observe the pointer movement at all. So, this is the meaning of the sensitivity. Now, how to compute the sensitivity of this bridge, or how to evaluate the sensitivity quantitatively, that I think we can do it with an example. Okay. So, let us take an example. So, we will take a simple example. Say we have a bridge which is like this, and this is the unknown. Okay. So, this is the unknown branch, and say we have the detector here, supply. Okay. So, for ease of calculation, let us take a simple example where say this P is equal to 1 kilo ohm, Q is again 1 kilo ohm, R is unknown, and S is once again 1 kilo ohm, where we get the balance. Okay. So, at balance, we find P equals 1 K, Q equals 1 K, S is equal to 1 K. So, this will imply that R, which is unknown, is once again 1 multiplied by 1 divided by 1 is 1 kilo ohm. So, this is very simple. Okay. But now, say this voltage E is given to be 10 volt. This is the supply voltage, and say there is the internal resistance of this source is negligible. Okay. So, we are neglecting the internal resistance of this source or this conductor, etc. Say this galvanometer has a resistance of Rg, call it once again maybe 1 kilo. Okay. So, we are just taking simple numbers. Okay. So, Rg is 1 kilo ohm, and say that the galvanometer is sensitive to 1 microampere current. Okay. So, that means a minimum of 1 microampere current must flow through this galvanometer, then only the pointer will move by an observable amount. If the current flowing through this galvanometer is less than 1 microampere, then we cannot observe any pointer deflection. The pointer will either not deflect at all due to friction, or even if it deflects, it will be very difficult to identify that deflection. So, the minimum observable deflection is obtained with 1 microampere current. Okay. So, now the question is, what is the sensitivity of this bridge? What is the sensitivity of this measurement? Okay. So, what is the sensitivity? So, for that, so we need to compute, we need to find minimum change delta R in the value of R, so that 1 microampere current flows through the galvanometer. Okay. So, if I call this current as I g, G for galvanometer, then we need to find out delta R such that I g is equal to 1 microampere. So, find delta R such that I g, which is 0 under balance, and now it will become 1 microampere. So, find out the value of delta R. Okay. So, how do we solve it? Solution. Let us call this point as A and this point as B, and let us take this as the reference point, that means 0 volt point for calculation. So, this point is at therefore 10 volt. Okay. So, this is 0, this battery has an EMF of 10. So, this point is at 10 volt. Now, that means the potential at B, call that VB, potential at B, it will be half of this 10 volt, because this is 1 K, this is 1 K. So, VB will be this value E, which is you can call as E multiplied by S divided by S plus Q. Okay. E and potential divider rule, which says divide by Q plus S and multiplied by S. So, this is VB. Now, if you put the values, it will come out to be, so this is 10 volt, 1, 1, 1. So, 10 by 2. So, this will be 5 volt, and this is fixed. Okay. So, this is fixed. Fixed in the sense, even if R becomes R plus delta R, this potential is not going to change. Okay. Now, what will be the potential at this point A, VA? VA is equal to how much? Now, VA, that will depend on the value of R. Okay. VA will depend on the value of R. If R changes, VA will also change. So, VA we can write as E, once again potential divider rule, multiplied by say R and divided by P plus R. Okay. So, this is the value of VA. Now, if R becomes R plus delta R, okay, so R becomes R plus delta R, R is changed by an amount, small amount. So, let us write R plus delta R. Here also this will become R plus delta R. Okay. So, this will be the value of VA. So, this is 10 multiplied by 1 plus delta R. This is 1 kilo ohm, and delta R we are taking in the same unit kilo ohm, divided by P is 1, R is 1. So, 2 plus delta R, where delta R is in kilo ohm. Okay. So, delta R is in kilo ohm, and this, okay, this is in volt. So, this is the value of VA. Now, what is the potential difference between A and B? So, V A minus V B, this will come out to be this quantity 10 into 1 plus delta R divided by 2 plus delta R, and VB is 5 in volt. So, this will become how much? This will be 10 plus 10 delta R minus 10 minus 5 delta R divided by 2 plus delta R. So, this 10 and 10 cancels. So, we have 5 delta R divided by 2 plus delta R. This is in volt. This is also in volt. Okay. Okay. So, and if observe that if delta R is 0, then VA minus VB will be 0. That means that will be the balance condition. Okay. And if delta R is non-zero, then this is the voltage which appears across the galvanometer here. Now, how much current will flow through this galvanometer due to this voltage? Okay. So, for now let us find out what will be the value of Ig. So, value of Ig we have to find, and let me copy this diagram. So let's now we have to find Ig. Ig is equal to how much? For that, we have to calculate the Thevenin equivalent of the circuit as seen by this galvanometer. Okay. So, for this we need, you can solve the same problem in different ways, but this is how I am going to solve. For this we need the Thevenin equivalent as seen by the galvanometer. That means from the terminal A and B, terminal AB or port AB. So, between these 2 points we will find the Thevenin equivalent of the circuit. Okay. So, we will find the Thevenin equivalent as seen by this galvanometer. Okay. So, let us draw the circuit first as seen by this galvanometer. So, let us remove the galvanometer and draw the circuit like this. So, this is, I am going to draw it like this: P, Q, R, S. Between this we have the source and the detector was here. This is point A and this is point B. Okay. So, the detector was here, and now, so we need 2 things. We need the Thevenin voltage and the Thevenin resistance. Now, Thevenin voltage VTH, this will be nothing but the open circuit potential difference between A and B. So, which is, if I remove this, then the potential difference between these 2, and here R has become R plus delta R. Okay. So, this is nothing but VA minus VB as we have computed before, because VB is always going to be 5 volt with respect to this point, and this potential depends on the value of R plus delta R. So, we have computed VA using potential divider rule here, and this is the difference between V and VB in the absence of this detector. So, this is same as computed before, 5 delta R by 2 plus delta R. Okay. This is V Thevenin. Now, what is R Thevenin? Thevenin resistance as seen by this. Okay. So, for that we have to remove this source. So, you have to short circuit this source, and if we short circuit this source, then starting from terminal A we have, so let us write terminal A and terminal B here. So, from A we have P and Q. So, let us draw it like this: P and then Q. This goes to terminal B from terminal A. So, this is P, this is Q. So, this is like this: P and Q. Okay. And from the middle point between P and Q we have this source, and there is another branch which is this R and S. Starting from A goes up to B. So, let us draw it like this: R and then S, it goes to B. So, here we have R, or actually R plus delta R, and S here, and the middle point between R and S, from here we have this source. The source is here. Okay. But while computing Thevenin resistance, we should short circuit the source. So, therefore, so let us short circuit the source. So, this is the equivalent circuit as seen from terminal A and B. So we have P, Q, R and S, and the middle point is sorted. Okay. So RTH therefore is the resistance between A and B will become P and R in parallel, because this is in this is sorted. So we will have P parallel R or R plus delta R in series with Q and S, okay, plus series Q parallel S. This is Thevenin resistance as seen from terminal A and B. So this, what will be this value? This will come out to be, so let me put the value. P is 1, R is 1 plus delta R. So this is basically 1 multiplied by 1 plus delta R divided by the sum 1 plus delta R, and this quantity will be 1 parallel 1. So that is 1 into 1 divided by 1 plus 1, so 2. Okay. So this is in kilo ohm, okay, in kilo ohm, because everything here is in kilo ohm. So I am not writing the unit, but I am mentioning it here that RTH is estimated in kilo ohm. Okay. So this comes out to be 1 plus delta R divided by 2 plus delta R plus this is half, and then this will become 2 plus 2 delta R. So check my calculations and please correct me if I make any mistake. 2 plus 2 delta R plus 2 plus delta R whole divided by 4 plus, or let me just write it like this, 2 plus delta R. So this is the Thevenin resistance. Okay. So I guess my calculation is correct. 2 plus 2 delta R plus 2, so plus delta R. So this is 4 plus 3 delta R divided by 2 plus delta R multiplied by 2. This is Thevenin resistance. Now what will be the value of Ig? Ig will be nothing but the current which will flow when we connect the galvanometer here. Okay. Now if we connect the galvanometer here in this circuit, the current that will flow through the galvanometer according to Thevenin's law will be Vth divided by, so this will come out to be V Thevenin divided by R Thevenin plus Rg according to Thevenin's law, Thevenin's theorem. Okay. So let us put the values. Vth is here 5 delta R by 2 plus delta R, 5 delta R by 2 plus delta R, and then here Rg is given, Rth is here 4 plus 3 delta R divided by 2 of 2 plus delta R, and Rg is once again Rg is 1 kilo ohm, right. Rg we have chosen to be here, Rg is given to be 1 kilo ohm. Okay. So this part, lower part, everything is in kilo ohm. This is in volt. Okay. So the unit will be like volt by kilo ohm. Okay. This is in volt, this is in kilo ohm. Okay. So now this we can write as 5 delta R divided by 2 plus delta R whole divided by, so this quantity denominator will be 4 plus 4 8, 4 plus 4 8, and 3 delta R plus 3 delta R plus 2 delta R is 5 delta R, whole divided by 2 and 2 plus delta R. Okay, this is volt by kiloampere, this is like milliampere. And now you can cancel this two terms. Okay, so this comes out to be 5 delta R into 2. Okay, so into 2 divided by 8 plus 5 delta R. This is equal to Ig, and we want Ig to be equal to 1 microampere. Okay, we want this equal to 1 microampere, which means, okay, so this is in milliampere. 1 microampere means 1 by 1000 milliampere, because so this is what we want, or this is the minimum detectable current. Okay, so this is the minimum current that we can detect. So the question we are asking that for what value of delta R this current will be same as the minimum detectable current, 1 over 1000. Therefore, now let us solve it. So this is also in milliampere, this is also in milliampere. So now we can write 5 into 1000. This is 10. Okay, so 1000 into 10 delta R. This is coming out to be 8 in 8 plus 5 delta R, right. So or 10,000 delta R is equal to 8 plus 5 delta R. So therefore, now this 5 delta R is much smaller than 10,000 delta R. So for just you can put the exact value and find the value of delta R, but using a calculator. Let me do it with an approximation because I do not have a calculator. So this will approximately, you can write this delta R is actually 8 by 10,000 minus 5, which is approximately 8 by 10,000, okay, ignoring this 10,000, okay, and this is in kilo. Okay, all our estimation was calculation was under the assumption that delta R is in kilo ohm. Okay, so this is the value of delta R is this much kilo ohm, which is same as 8 into 10,000 into 1000 ohm, which is 0.8 ohm. Okay, so if I haven't made any mistake in my calculation, this implies delta R is approximately equal to 0.8 ohm. So this is the minimum change in the unknown delta R which we can detect, due to which the pointer will move. So we say the sensitivity of the measurement is 0.8 ohm. If R is changing by an amount less than this, it will cause no pointer deflection, we cannot detect it. So in this video, in this class, we have discussed 3 concepts. Firstly, accuracy, then the resolution of the Wheatstone bridge, and finally the sensitivity of the Wheatstone bridge. And we have done a thorough calculation. We have taken an example and have shown you how to do the calculation thoroughly. Thank you.